All aboard the AstroTour. Today, we will be going on a tour through the solar system to uncover how our 8 planets experience seasons. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. The white lines you see are the rotation axes of each of our planets. A vertical line means that the planet is spinning upright. You'll notice only 2 of the 8 planets are actually spinning upright, Mercury and Jupiter. 4 of the planets are tilted nearly 25 degrees. And when I say tilted, what I mean is the planets orbit around the sun, and this is the angle of its spin axis relative to the direction of its orbit. So Earth, Mars, Saturn, Neptune, tilted by 25 degrees. Uranus is tilted by 90 degrees, spinning almost on its side as it basically rolls around the sun. And Venus, the bright one here, I think is also quite surprising. It spins upside down with a near 180-degree tilt, meaning it spins backwards. So what causes these tilts is the question that we're going to explore today. For example, for Earth is tilted by 23 degrees, and the reason we think this is that a long time ago, a large object smashed into Earth, creating a violent collision, tipping Earth, and the leftover debris after this collision formed the moon. So these tilts tell us stories about how our planets form and evolve, and as we begin to explore different planets, we'll find new stories uncovering how they form. And then, and then we will blast off to infinity and beyond, where we will be in the company of the many planets outside our solar system. Do people have an idea of how many planets there are beyond our solar system? Lots. If you want to know a rough number, you can count the gray dots in the background, which is a representation of how many there are. There's over 5,000. There's more and more being discovered almost every day through large telescopes, space telescopes, and so on and so forth. And so these tilts, so as we discover the tilts of planets in our solar system, planets beyond our solar system, we'll hopefully uncover the seasons of distant, possibly alien worlds. And so without further ado, to the bus. We'll be taking the Magic School Bus on an interplanetary journey through the solar system. And but worry not. This is actually not my first AstroTours. My first AstroTours was exactly 10 years ago. Oop. So in March 2015 was my first AstroTours. I was 15 years old in high school. And what you see is there are a bunch of demos that you'll see later. This is, I think, using the Xbox Connect, where you can like kind of travel through the solar system using your hands. I think you guys can still do that today, if I'm correct. James is nodding, so I think that's a yes. And you know, when I was this age, I really enjoyed stargazing, and I thought to myself, wouldn't it be great if you could make a living looking at the stars? So zooming forward to 2024, well, last year. 2024 is, in my opinion, I think, my favorite year of astronomy. We were nearing the solar maximum, meaning that the sun was getting more and more inactive with a cycle of 10, 11 years. And in particular, we were seeing record-breaking examples of huge solar flares, which we got to enjoy by seeing all these auroras. So aurora hunting with my mom. We saw the solar eclipse in 2024, and there's also a planetary alignment of 6 planets. So these events, in particular the planetary alignment, remind me of a conversation I had many, many years ago with my mom. She asked, "Son, why are you looking at all these dots in the sky?" To which I said, "Each of these dots are different worlds. And I think it's really the thought that counts." And reflecting on this experience in the past decade, I feel very fortunate to have the privilege of following these worlds. And today I'd like to tell you their stories. So today I'd like to dedicate this talk to my mom and dad who are here in the audience. Thank you for being here. Yeah. So, who've always encouraged me to follow my curiosity, chase my dreams, and I'm grateful that they've been supporting me every step of the way. All right. So let's start from the beginning of the story. So a crash course into how planets form. So this is what the solar system looked like billions of years ago. There's no star, there's no planets, just a ball of gas and dust. This ball of gas and dust is going to collapse due to its gravity. And as it collapses, the gas is going to feel more pressure. And as the gas feels more pressure, it's going to heat up and heat up until it reaches 10 million degrees Celsius, at which nuclear fusion will begin to ignite. This is the birth of our sun. But not all the material goes into building our star. About 1% of the leftover material will remain in this rotating disk of dust and gas and begin to form what are called planetesimals, which are rocks that are 100-meter to 100-kilometer sized and are the building blocks of planets. So you'll have these basically rings around the sun of material that will then, over time, begin to gravitationally interact with each other. They'll either merge together or some will get ejected out of the system, eventually condensing and creating the 8 planets that we see today. And this is a very simple picture of how planets form, and you might get the idea that we've solved it. But planet formation is actually still a very active area of research, one that I'm very fortunate to be a part of. And some of the ideas that are still open questions are things like, well, you have all these planets. How come some are so big? How come some are so small? How long does it take to get from step 1 to step 2, 3, 4, and 5? And did the planets actually form where we see them today? Some theories say that Uranus, currently the 7th most distant planet from the sun, actually formed the furthest away and at some point switched with Neptune. So there's a lot, that's to say there's a lot of details. This is still an ongoing area of research. But for now, I'd like you just to imagine this simple picture. Planets form on happy circular orbits around the sun. And with that, well, what should we expect for how the planets spin? So what do we expect? We expect that because planets form in the disk around the star and all the material is orbiting the same in the same way, planets, since they're born in there, should also be spinning upright. Surprisingly, that's not the case. So is there something we gravely don't understand about how planets form? Well, the current understanding is that planets do form upright, and then something happened to each of these planets. For Earth, it got hit by a massive object, tilting it over, but that's not exactly the case for all these planets. So the way I think of these planets, so these planets are not only tilted, but they're also 3D objects that spin, and they spin at different rates. For example, Earth takes 1 day to go around Earth, but Jupiter the largest planet in our solar system, spins with a day of 10 hours. And just to clarify, the angle that you see in the top, 0 degrees, 177 degrees, is the tilt I'm talking about of the spin axis relative to the planet going around the sun. I like to think of these planets as spinning tops in the sky. And what better way to think about spinning tops than with these guys? Can I show? I'd like to see a show of hands of who knows what these are. Oh, wow. Okay. I was under the impression that most people coming to this would either be high school students or people that are retired, so it misses the age where Beyblades were exciting. But I'm glad that people are excited by this. So, uh, what might we have in this brown bag over here? All right. Whoop. So we have this yellow one, which is called the Arrowhead Wizard 480B. And we have this red one here, which is the Scythe Incendio 460T. I would like one brave volunteer to help me with the demo. Uh, anyone like to anyone here want to play with Beyblades? Whoop. All right, over here. Yes, yes. Yes, with the Gap sweater, please. Okay. Okay, okay. Yes. Right. What are Beyblades? You'll see very quickly. So Beyblades are spinning tops, and most tops you kind of twist with your hands. A Beyblade is a little bit more intense because you can get these things to spin really, really fast by using these two pieces of equipment right here. So this white piece here is what we call the launcher. This one is the ripcord. And yeah, sorry, what's your name again? Swan. Swan? Okay, let's give a round of applause for Swan. Thank you, thank you, thank you, Swan. Okay. Yes, please, come over here. Okay, so, oh, perfect. Okay, I hope you guys can see. So yeah, so here is just a simple old baking sheet, and we're going to be spinning the Beyblades on here. So have you? No. Okay, okay. All right, so I will demonstrate once, and then we'll see how it goes. Okay, so okay, so yeah, so would you like the red one? The okay, yellow one? Okay, perfect. Okay, so with the launcher in hands, so grab the launcher in your left hand, ripcord in the right hand. Okay.
Okay, sure.
Yep. Okay. So the ripcord is going to have some teeth along the side. So you want the teeth to be on the left side, and then place it through. There's a little hole. Yep, 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 yep.
Okay.
Perfect. Okay.
Okay. Mine's going up. Yours?
Yeah, yeah. They're, I don't know. They're, yeah, it's perfectly fine. So yeah, slide it in. Yeah, all the way here.
Okay.
Yep, yep, yep. And so just to practice, what you're eventually gonna do is you're gonna pull it like this. Yes, and that's gonna cause the Beyblade to spin really, really fast. So. So you might be tempted, or at least I was very tempted at first, to rip it like I'm starting the lawnmower.
Okay.
But if you do that, this one is going to fly really far away. So instead, I want you to think of it as like strumming a violin. So just like smooth, like exactly like a smooth continuous motion. Yes, perfect. And so and while you pull it, so we want the launcher to have the to be horizontal so that the Beyblade, when it lands like straight like this. Yeah, so we'll do it together. It's like violin,
Violet.
violin. Yes, okay. So yeah, yeah, like a violin. Do people know what is typically said when we play the Beyblade? Okay, let it rip. Okay. So when I say let it rip, we go 3, 2, 1, let it rip. Okay, perfect. Okay, so I'm gonna do it once, and then we'll see what happens, and then I will let you try after. Okay. So, right. So with the Beyblade, you're gonna place it under, and then turn it um, clockwise. So just and don't do anything. Let me go first, and then we'll see what happens. So 3, 2, 1, let it rip. Wow. So the planet. So you should imagine the Beyblade is like a planet, and this Beyblade is gonna basically keep spinning straight up, just like a planet is. Um, and what you should imagine is, planets spin like this, and they will always spin like this because they form like this until something happens that will topple it over. Okay, so now I want you to try. Okay, yes, okay, so,
Let it
okay, 3, 2, 1, let it rip. Okay, you can go. Yeah, no worries. Okay, yep,
I can do this.
yep, okay. 3, 2, 1, let it rip. Oh, sorry. I'll let you say it. I'll let you say it. Okay, so yeah, so the trick with why it's falling off is if you hold it to the side, it kind of doesn't really attach. So you have to hold it like, yeah, so like, yeah, have it horizontal. Yep.
Okay, one more try, then somebody's going to come and help.
Okay, yeah, perfect. Okay. Hey! Perfect. All right.
Saturn.
You can think of it as Saturn. You can think of it as is this going to be Saturn for you? Okay. So, because now that we both have it working, we're going to simulate what's happened to some of the planets in our solar system. Okay? So, I want you to do the same thing. You're going to do it, and then I'm going to wait like 5 seconds and then play my Blade, and then we will see what happens.
Break. Yes.
Yeah.
Got it. Sorry.
Take your time. All good.
Okay, horizontal. Wait, no. Put it in. Horizontal. Turn. One more.
Yeah, 1, 2, twice good. Yep. All right. And then I'm going to go 3, 2, 1, let it rip. Okay. So maybe the planets don't talk to each other. Oh, so what you see is that the planets are starting to wobble. They're starting to get a bit of a tilt. Yeah. Oh. So they hit each other, but they don't completely topple over unless it's a really big. So for Uranus, one of the planets is kind of really spinning on its side. Oh, and so okay, so let's give it a round of applause. Okay, thank you so much. Thank you so much. Okay, so yes, let it rip. Sorry, this is one. I have one more. Okay, one more demo to show. So right, so this is one of the ways we can tilt a planet. How else can we tilt a planet, or how else can we tilt a Beyblade? So one way we can do so is instead of the two Beyblades hitting each other, planets feel a gravity between each other, and when the planets feel gravity towards each other, that can affect its motion. And so the planets, um, they spin, but they also have their own orbits. So they both travel around their sun. And if you imagine like one planet's orbit versus another planet's orbit, these orbits can talk to each other and cause their orbits to wobble slightly. So the picture I had before, where all the planets are forming in a flat disk, is not perfectly correct. All the planes of each orbit are offset by like almost a few degrees, but that's enough. That's actually enough to cause some effects in our solar system. Um, so now what I'm going to do is I hope this works. Okay, so I'm going to run the Beyblade. Okay. So now if I start shaking the pan below, ooh, let's see if that works. Okay. you can kind of see it start to wobble, tilt. And so this is one way that say the yellow planets can feel the effects of the red planet even though they don't talk to each other. So they don't hit each other, but they talk to each other through the effect of gravity through their orbits. Okay, so thank you for in hope you guys enjoy the Beyblade demo. All right. I know I will be playing with this a lot in my office in the next week to come. Okay. Ah, thank you. Thanks so much, Nolan. Okay. Right. So hopefully you guys are convinced that planets can tip over and do all sorts of weird things either by getting hit or through some long-range gravitational interaction. Okay? Um, so the next question is, okay, these planets are tilted. So what? For Earth, it's tilted by 23 degrees, which gives us seasons, which explains why it's so cold in the winter and why it's so cold when we walk out of Union Station in February. So next, oh, second. I'm going to show an animation here. So this is Earth going around the sun. And so the red line is the latitude of where Toronto is. The tilt axis is pointing slightly angled towards the sun, which means that in the summer, it's really hot because we receive a lot of direct sunlight. And as we go through the seasons, now Earth's tilt is not really pointing towards or away from the sun, but kind of like parallel. And so that's when we have either fall or spring. If we wait a few more seconds, now come in the winter months, where the axis of Earth is pointing away from the sun. But what if we were in the southern hemisphere? So in the southern hemisphere, the seasons would all be flipped. It would actually be summer here, winter over there. Another way you can see this is whoop, from Earth's point of view, which is on the top right. So as we approach summer, we're receiving more direct sunlight. On the top right, it looks like the sun is basically perpendicular to the surface of the Earth. It's not perfectly perpendicular because we're not near the equator. And now as you wait for things to get colder because it's really hot in the summer, eventually what you'll see is that sunlight is now beginning to graze where Toronto is. And so you have less direct sunlight. These sun rays are looking more horizontal, and that means the Earth is not going to be heated up as much. All right. So to recap, I also have a globe here to help illustrate this more. So I need one more volunteer if anyone's interested. Yes, over here on the right. Yes. Thank you. Let's give a round of applause. Thank you. Yes, and your name is? Jeremy. Nice to meet you. Okay. So you will be my son, and I will be your father. Okay. So okay, first thing before I hand this to you, please do not point it at the audience. Okay. Okay. Okay, I'd like you to stand over here, and your job is to point towards me. Okay. So, so this is Earth. I put a little sticker where Toronto is. So you might notice that this thing is tilted on its side, and a lot of globes are. It's not just because it's pretty, but this is how we think Earth actually is as it goes around the sun. So if I'm over here and I'm in Toronto, what season would it be? Summer, perfect. Yes, because the Earth's axis is tilted towards sun, my sun. And as we go over here, we have winter. Winter. Right. But what happens when the tilt of your planet is not is not just 23 degrees, but more, say like 90 degrees? Well, we'd all fall off. No, we wouldn't fall off, but there are some planets, such as Uranus, that have this extreme tilt. And so Uranus not only has this extreme tilt, it also is way, way further from the sun than Earth is. So it's all the way over here. And so as it's spinning, it has a winter of 40 years. As well, if you're say you're in Toronto on Uranus, so over here. So for 40 years, the sun won't rise. And so that's going to be a really, really depressing time. Whereas in that's in their winter time, but whereas in their summertime, the sun will be up for 42 years. That's a sense of how seasons can be different when you have a different tilt. So thank you so much. Let's give a round of applause for my son. Thanks so much. Okay. All right. Okay. Right. Yes. So we're on Uranus and our first stop, and we think why Uranus is tilted is due to a violent collision, which basically tips Uranus over. What you'll kind of notice actually is that this collision is not just any collision, it's a grazing collision where it hits Uranus kind of like a little bit on its edge, causing it to tip over a lot. We think Neptune, which is tilted only by 25 degrees, got hit with more of a face-on, like middle sucker punch kind of collision, which tipped it a lot, which tipped it less. Right. So on to the next. We're going to go to Saturn. Welcome to Saturn City. And so here the story is that we don't think something hit Saturn. Saturn's really, really big. It's really hard to tip over. We think it's due to some long-term gravitational interaction with Neptune, which is what I tried to show with this demo here, where I'm shaking the pan, allowing one Beyblade to talk to another Beyblade through their orbit. In the same way, Neptune feels the gravity Saturn feels the gravity of Neptune, causing it to tilt. So let's keep going. We don't have much fuel left, and the nearest planet outside our solar system is 4 light years away. That's 500,000 times further than Saturn is to the sun. So we can't go to these distant planets. So how are we going to get there? Well, we use our telescopes to look at these distant planets. And so this is a video showing the diversity of some of the planets we've seen in our solar system. So the dotted lines are all of Earth's planets. And these are a bunch of planetary systems, real planetary systems to scale, showing their orbits, the size of their planets, how hot and cold they are. There's this big wealth of diversity of planets, and we want to know, well, how are these tilted? It's really hard to measure these. I'll briefly go over how we can actually do such a thing. So you have your star, you have your planet, and we can't it's really hard to just take a picture of the planet, see which way it's pointing, because the star is millions of times brighter than the planet. So we can only do this for the biggest, brightest, and baddest planets. These are my favorite ones. These are called super Jupiters that are 10 times more massive than Jupiter. So we can find its orbit by using really large telescopes called the Very Large Telescope. And over many years, we take pictures of the planet going around the star in order to find which way its orbit is pointing. Similarly, to get a spin, we need space-based telescopes in combination with ground-based telescopes, because these planets are really only 1 pixel in the sky. And so we can look at how the planet spins by monitoring it for hours, many hours, 10, 20 hours. We saw Jupiter spins for 10 hours. And from that, once we get all this information together, it's a matter of doing the math, taking care of all the angles, and we can get the tilt. So what I tell my friends is that if I'm not getting a PhD in astronomy, I'm getting a PhD in trigonometry, because there's so many angles that you have to take care of. Okay, so what do planet tilts look like outside our solar system? So one of the first objects I looked at during my PhD is VHS 1256b. This is an artist's rendition of the planet. This super Jupiter is around 2 stars, so it orbits kind of like Tatooine. This is more of a realistic picture of what it looks like using a technique called direct imaging. This is a picture from the Discovery paper in 2015, where what you see, the big circle is a star, the little circle is the planet, and you actually can't tell that there's actually 2 stars there because technology wasn't the best at that time. And so with my PhD work, we applied for telescope time using the largest telescopes in the world for both on the ground and in the space to figure out how this planet spins. And our main conclusion is that this object is a super Jupiter with a Uranus-like tilt. So instead of like this, I think it actually looks more like that. So what do we expect in the future? So you guys may have heard about what this thing is, the James Webb Space Telescope. It looks not in visible light, but an infrared light, which is best for planets because planets that I care about, or these huge planets, of which there's only like 25 we've discovered so far, glow the brightest in infrared light. And what I'm the most excited for is that the James Webb Space Telescope is planned to look at this object, a different object. It's called Beta Pictoris b. These are real images of the planet using direct imaging, an animation from like 2005-ish to 2018, showing the motion of a planet going around the star. And what you can't see actually is that there's 2 planets in the system. The second planet is behind this black circle at 3 AU, where an AU is an astronomical unit, basically the distance between the Earth and the Sun. Why is there a black circle? Basically, a trick astronomers can use to look at planets is called using a coronagraph, which is basically like you have your planet in the sky, you have your star in the sky, and you say, what if I just put my hand in front of the star so we can't see it? Then the planet will appear to be more visible. Right. So we simulated what tilts could come out of a observation, found that this tilt is likely to be misaligned, and our best explanation is that there must be some kind of moon, and that this object is tilted like Saturn. So in the same way that we think Saturn talks to Neptune through gravity, we think that this planet talks to its inner planet, and the strength of the connection of how well they talk to each other isn't strong enough. But if we put a moon around the planet, then then the math says it works out. This is not like we found anything, but it's basically saying like theoretically, well, could using James Webb Space Telescope to find how planets are tilted help you find the first exomoon, because we haven't found any moons outside our solar system yet. If you'd like to hear more about this work, there's actually a really great YouTube video by Kai Planet. I don't know who Kai Planet is, but if Kai Planet is in the audience, thank you for this video. He describes a lot of the findings of the paper, does a really good job in explaining the ideas of these moons and these planets, and it's something that I really thought was a great video. And so yeah, check it out if you're interested. I thought it was really cool. So let's recap our trip together. So here's a family portrait of planet tilts. And if there's one thing you take away from the talk is that planet tilts tell stories about how they form. We didn't get to go over all the stories, but we did talk about Earth, Uranus, Saturn. Um, these tilts tell stories, so naturally we can ask, what do tilts look like for distant planets, distant cousins of the solar system? We visited VHS 1256b, a 10 Jupiter mass, 10 Jupiter mass planet that leans sideways, like Uranus, showing us that distant planets might not be so different from ours. With the James Webb Space Telescope, we will visit Beta Pictoris b and see if an exoplanet tilt could imply something about an exomoon. So, to conclude, as an astronomer and astrophysicist working on exoplanets, I think the future is bright. We'll find new planets, new tilts, and new stories, giving us a better picture of how our solar system formed. What is our place in the universe? Is there life out there? And are we the only ones who complain about the seasons? Thank you. Oh,
All right.
no, no, no. Yes, and please feel free to email me if you have any questions. I also like to thank all my friends and family that came out to support me.
All right.